Let's continue our discussion on design principles. We talked about a few metrics to measure the quality of design. Let's continue further from there. We are interested in creating better quality design, but one way we can create better quality design is by avoiding some poor design practices or bad design. Bob Martin wrote about this in several articles. He talks about 7 perils of bad design. Let's go over them here. The 7 perils of bad design, the first one he talks about is rigidity. And then he identifies a few things like fragility, immobility, viscosity, needless complexity, and needless repetition, and finally opacity. Let's talk about each one of them and understand what these things actually mean. And we'll also talk about what causes some of these as well along the way. So let's talk about rigidity first. But before we talk about rigidity, I want to talk about 2 different words and slight difference in meaning. One is stability and the other is rigidity. Now, the distinction between these two is stability is where there is really no reason to change. Rigidity is where even if there's a reason to change, you are going to be unwilling to change. Now, why would you be unwilling to change? The reason we would be not willing to make a change to a design is we are afraid of the ramifications, the consequences of that change. Let's think about some of these things for a minute. What would become really stable? Well, something that has really no reason to change is stable, and we can clearly identify what would become really stable. For example, interfaces are really stable. Now, the reason why an interface is stable is an interface really has no implementation in it. And as a result, there is not a whole lot within the interface that causes it to change. A good interface should not depend on a concrete class. It either should have no dependency, or if it does have a dependency, such dependency should be on yet another interface, which also in turn would be stable. So stability is where we have really no reason to change. Rigidity, on the other hand, is there is reason to change, but we are extremely reluctant to change, and that's what rigidity really means. Now, a class typically would have reasons to change. Now, on the other hand, you are afraid, let's say, to change a particular class because if you change that class, it may affect other pieces of code that depends on it. You are going to become more rigid with that change because you don't want to cause a ripple effect of a lot of different changes. So to understand what causes this rigidity versus stability, let's consider a few different scenarios, if you will. Let's consider for a minute that we have a class C1, and let's say this class C1 depends on, let's say, 7 classes. Now, these two are concrete things on both sides. C1 is concrete. All these classes that it depends on are concrete as well. Let's think about what's going to be the state of this class C1. If any of these classes were to change, and classes by nature would potentially change because they got implementation and they got to go through evolution over time, and if any of these 7 classes changes, then the class C1 is going to end up changing as well. So if you were to draw a little diagram, you could say here's C1 and lines going out to these other classes. And so if the lines are going out from a class, the class is going to be relatively unstable because what it depends on is going to change, and as a result, the class would have to change. So if a class depends on another class, naturally it's going to become less stable than the classes it depends on. On the other hand, let's say we have a class C2, and the C2 is used by several classes. In other words, several classes, let's say several classes over here. So all these different classes depend on, let's say, depend on C2. So in this case, what's happening? Well, all these classes are literally, so to say, sitting on top of the class C2, and the arrow is pointing towards C2, and they're all saying, I am using the methods and the properties in this class C2. There's such a weight sitting on top of C2, like a basement in a building. Well, that better become very rigid, because if you were to change what's in the bottom, that's going to shake all the classes that depend on it, and that's not going to be really fun at all. Really bad things can happen in this case. You probably have seen this. You probably went to an interview in a company and you're talking to these people in the department that you're going to work in, and then they say, let's go to lunch, let's grab a quick lunch. They take you to the company cafeteria, and you're sitting and having a meal, and then all of a sudden you realize that way back in the corner over there, there's one programmer sitting alone, facing the wall and eating quietly. And then you lean over to your potential colleague and say, hey, who is that person over there sitting alone? And your colleague leans over to you and whispers in your ears, we don't talk about him. He changed a very critical class in the system, and that affected a lot of our code, so he's on timeout, right? So bad things can happen like that, and then you end up spending quiet time at the cafeteria. So you don't want to really get to that point where you really change a piece of code and affect all the class that depends on it. So the point really is, rigidity comes from dependency. If more classes depend on your class ends up becoming rigid. On the other hand, if your class depends on a lot of other classes, your class becomes unstable. So you can then picture this. Here's your class. You have dependencies coming here on this side, and you got dependencies going out on this side. If any of these change, your class would be affected. This would become unstable. And if you have things depending on you, if you change, these will get affected. So you're going to make this rigid. So now, so to say, you're stuck between a rock and a hard place. If these force a change on you, you are really worried to keep this change really minimum so you don't affect the classes that depend on you. But given a scenario where you have a class and this class doesn't depend on anything at all, but other classes heavily depend on it, those kinds of classes are called utility classes. Utility classes, for example, units of measure conversions. Given a unit of measure in, let's say, English unit, you want to convert to metric unit. Hey, how many really miles are in equal to kilometers, for example? Well, these kinds of unit of measure conversions, they don't really depend on anything. So they are the bottommost class, but they get used very heavily in applications. If you come in and modify something at that layer, it can render a lot of code really broken, and you're not going to become very good friends with your team if you do that. So that class is going to become very rigid. Interfaces also have rigidity in that way because interfaces get used from all over, but the difference though is interfaces are stable and not rigid because interfaces have no reason to change, and of course because they don't have any reason to change, they are very stable, and because they are stable, they don't really affect classes that depend on them. On the other hand, a class has a reason to change oftentimes, but it's very reluctant to change because it'll affect those classes that depend on it. As a result, the class is rigid. So that the diagram looks about the same. Classes coming, arrows coming in, but if this were an interface with arrows coming in, this interface is stable, but if this was a class with arrows coming in, the class is rigid. Because an interface has no reason to change, a class does have a reason to change, but it's reluctant because of the dependencies coming in. So when it comes to thinking about the design and the quality of design, we have to think about rigidity. Rigidity is when it is very difficult to it's very hard to change. And because if you make such a change, it will result in a cascade of changes through the system, and you don't want to really encourage that. So as a result, the design becomes very rigid. That's a smell of a bad design. So as much as possible, we want to reduce that rigidity in design. Now, whether a particular dependency is causing stability or rigidity, we only can know whether it is stable or rigid by looking at whether that is a class or an interface. If it is an interface, it contributes to stability. If it's a class with dependencies, it contributes to rigidity. So there are two things we have to consider in evaluating this. We have to consider the dependencies that's coming in. We also have to look at whether this is an interface or a class. An interface with dependencies is stable, and class with dependencies is rigid. So we got to consider both the dependencies and also the interface versus a class in making this particular decision. The next peril here we should think about is fragility. Fragility is where a small change would quickly end up breaking your code. Now, I'm sure all of us have worked in systems where we have a change request, you start making the change, and when you make this change, something here doesn't work anymore. You change that, and suddenly this doesn't work anymore, and now you're in a mess of change, and you say, it's going to take a few hours for me to get this code back into shape and go through and make all these changes. That's a sign of fragile or fragility in design. Reminds me of experience back in time. You're working on a piece of code and you barely make all the code to work, and then you quietly step back and say, the code is working now, don't touch it. This reminds me of in my youth, and I'm sure everybody has done this, you probably have spent your time playing with the house of cards. So you take the cards and then you start building cards, you put them in the shape, and then you put a card on top of it, then you build a card on it, and you're building, and it keeps growing up in size, and as it becomes bigger and bigger, you're worried it's going to fall. And if somebody opens the door or a window, you say, hey, don't do that, and you're in whispers, you don't want a draft to bring that down. And while they're building this house of cards, somebody suggests, why don't you add this card here or remove this card from here and put it there, and then you cringe. It's like, oh, don't touch it, it's going to fall. And then of course somebody makes one small change and the entire things come collapsing down. And we grow up and build systems, and we end up building systems, unfortunately, like that. And it becomes extremely fragile. You get the code working, and then you quietly back out of the system and say, hey, the code is working now, don't touch it, because I just put it back together. That's a sign of a very fragile application. And fragility is really hard because one of the things we have learned over time is making change to software is extremely critical. And if you're not willing to make a change to software, we cannot be agile, we cannot respond to change. And the only thing we know is the change is the only constant, as Heraclitus said. So we must be able to afford these changes. And with the system which is very fragile, it's expensive to make these changes, and we don't want to really have such kind of expense. But where does fragility come from? Well, fragility comes from instability as well. So if your code is concrete and it depends on other concrete classes, if any of these classes change, your code would have to change. And with lack of rigidity, this can become fairly unstable. Well, a great example of a code that is very fragile oftentimes is UI code. A UI code, which is designing the user interface, often depends on code below. If any of the code below changes, the UI code would have to change. And almost anytime a user or customer walks by, they want to change your UI as well. If they walk over and say, I don't really like that, I want this to be different. And if you say, well, I really don't want to make the change because if I make the change, other code will be affected. And they ask you what other code will be affected. Well, really nothing, because nothing depends on this. Well, then go make a change to it. So usually that code can be fairly fragile. Also, a code that depends on concrete types can become fragile, not only because the concrete type can change, it's also we may from time to time decide we don't want that implementation, we want something else. Another thing that causes fragility, by the way, if your class, your code, your function is not cohesive. So if your code is not cohesive, the opposite of the good practices, very low cohesion and high coupling causes fragility. Low cohesion. So your code is big, is not narrow and focused, but diluted, does too many things. What's going to happen to that code that's doing too many things? Well, it's going to change more frequently because it's doing too many things. However, if a code is narrow and focused and does one thing well, the chances of that changing is very less, and so that code is not going to be as fragile. So high cohesion lowers fragility. High coupling increases fragility. So cohesion is inversely proportional to fragility. Coupling is directly proportional to fragility. So that is another thing we can keep in mind. If you want your code to be less fragile, then make the code more cohesive and low in coupling, then automatically it becomes less fragile because of the inverse proportionality and proportionality I talked about, comparing it to cohesion and coupling respectively. So fragility is another design practice we should really keep in mind, design smell we should keep in mind. Then comes immobility. Immobility is where it's very hard to reuse the code. Now, reuse that is the holy grail in software development. We don't want to create something that's usable. We want to create something that's reusable. How many times have you heard developers come and tell you? How many times you have told other developers, I want to write this because this is going to make the code more extensible. I want to write this because this is going to make the code more reusable. That is the way we deceive ourselves. So do not aim for ultimate extensibility and reuse without knowing what it really is and what actually makes code really hard to reuse. Well, if you really think about it, coupling makes reuse really hard. If my code is dependent on this other piece of code, if you want if you want to reuse this code, well, I can't really take this code and give it to you because it's got dependency on this code. I got to send you this code as well. I was working in a product where one day my boss comes in and declares, I was talking to this other department and they are developing this particular application within the same company, of course, and they are really interested in using this kind of algorithms. And I just told them, you don't have to reinvent the wheel. We already have that as a component and we will be glad to share our component with you guys. And I listened to it and said, well, thanks for volunteering to do that. But all I want to know is, what is that component you keep talking about? Well, the point is, yes, we were doing this algorithm, but unfortunately the design was not created in a way this particular algorithm was in a module. So when they came in and asked for it, we give them a class. Within 10 minutes, they say, oh, code doesn't compile. It wants this other class. And within a few minutes, the entire application code base is on their side because of the coupling. So think about this for a minute. If your class, let's say you have a class on your hand, and if your class, let's say, I'll call it my class, and my class depends on this class, other class, let's say. Well, in this case, how in the world can I reuse my class in another place without also taking the other class with me? Well, if my other class is very ingrained with a certain implementation detail, unfortunately, it doesn't become so easy to reuse. Let's look at one example. Let's say my class over here is performing order processing. So order processing is going to be, order processor is my class, and it is going to talk to credit, let's say, service XYZ. Well, in this case, let's say another project or a different division is interested in the same order processing. So they want to reuse the order processor, so I readily give them the order processor and say, here you go, I'm glad to help you. Here you can reuse this order processor. Well, within minutes they call me and say, I'm sorry, I'm not able to use the order processor. It says it wants a credit service XYZ component. Oh, of course, sorry, we forgot to give you that. Here you go, I'm going to give you that as well. Now, collectively, these two are reusable, but this alone is not. Except a few minutes later, they call me and say, well, we got a problem. We are not going to use a credit service XYZ at all. We are going to get payment processed through a different service entirely. What gives? What do we do? Well, now they have to physically modify their copy of order processor to use a different service. Well, the minute they start changing this code, that's called copy and paste reuse. And that is not reuse, that's called code abuse. So they're not reusing order processor, they're copying and pasting and changing it. A few months goes by, you make an enhancement to the order processor. Sorry, they cannot get that change over here because that's a different order processor now, and it is more expensive to push the changes across and make it reusable. If the component is really reusable, you should be able to release a new version of the component and they should be seamlessly able to upgrade it and continue using it. So what can we do about this? Well, one way you can manage this and make it more reusable is you go back here and say, I am not going to depend on the credit service XYZ. Instead, I'm going to depend on a credit, let's say, service. Now, credit service is an abstraction, but more of an interface. And the way we could create this one is we could say that this particular credit service that we are creating right here is going to, let's say, extend or inherit from that particular credit service interface that we have created right here. So I'm going to use my artist skills here and show you how that inheritance hierarchy looks like. So if you notice over here in this case, we have, look at this as a triangle, if you will. So that's an inheritance hierarchy. My credit service XYZ depends on the interface credit service. Now, when your other department colleagues want to reuse order processor, you readily give them the order processor as a binary and say, go ahead, use the order processor, and it depends on the credit service. All you have to do is either come back and ask for our credit service XYZ if you want to use that, or go create your own implementation of the credit service that you want to use, and this would be credit service IMPL2, and that as long as that implements that same interface, very same story as we saw here, but notice the beauty of this particular solution. The beauty of this particular solution is that in this particular case, our credit service is exactly the same, so this part is entirely reused in binary form, and as a result, they only have to potentially implement that part for a different implementation they want. Now, in this case, if you make changes and evolve order processor and release a new binary of your code, they can readily use that because they haven't modified it, they simply are reusing it. So in other words, what we are talking about here is that when it comes to the code, we can see that immobility comes from tighter coupling. So the more tight coupling we have, the less mobile or reusable the code actually is going to be. So in this case, the reuse is inversely proportional to the level of coupling. The more the coupling, less the reuse is, less the coupling, the more reusable the code can become. And when we say less coupling, it's not only not having the coupling, but also loose coupling. And we talked about this before. Depending on an interface is loose coupling compared to depending on a class, and that comes to immobility. The next feature to talk about, the next smell to talk about is viscosity. Viscosity is where it is easy to do the wrong thing and hard to do the right thing. And we have different kinds of viscosity. We got technical viscosity, we got environmental viscosity. Now, go around and ask people how many of them use version control system. You'd be surprised. There are still people who don't use version control to store their things. Now, go around in your own organizations that you work in. As programmers, are all your code in version control? And I'm hoping they would say, yes, of course, all of our code is in version control. Yeah, that's great. What's the benefit? If the code is in version control, you can go wild and make change and experiment. If it really works, check it in and keep it. If it doesn't work, discard it. Bring the copy that works from the version control and you move forward. This gives you the agility. You can also go back and look in the history and say, 6 months ago we had this version of code. We wanted to use some part of that we discarded earlier, but looks like some of that can be used now. You can bring it back and use it as well. Checking in code frequently removes fear of change from our mind. A lot of different benefits. Then walk a little bit further and go to your testers and ask them if all their automated tests and test documents are in version control. Go ahead and ask them and find out. You would be surprised. Even in organizations where programmers keep the code in version control, testers do not keep their test automation scripts in version control. They don't keep the test documents in version control. Shocking, isn't it? But why wouldn't they? Well, because nobody told them to. Then walk a little bit further and go to your business analysts and your managers, product owners, and your project managers and say, artifacts you create, your requirements document you create, all of them are in version control, right? And find out what the answer is. You'll be shocked. Most of the time the answer is, well, it's in the shared drive, it's in the SharePoint. Well, is it backed up? Is it in a version control? If I want to go back and pull up a version and look for what change I made 3 weeks ago, how would I do it? Well, you'd be shocked about these answers. When you have these things, why don't people put code in the version control? Oh, it's easy to be disorganized. It's easy to not have discipline. It's easy to do the wrong thing. But it's really hard to do the right thing. But once we bring in these practices, once those become the way to do stuff, you would think very differently moving forward. Now, at the same time, for example, at the code level, let's think about an example. Let's say we have code duplicated everywhere. Now, why do we duplicate code? Well, duplication code is the wrong thing to do, but it's easy to do the wrong thing. Why did we duplicate the code? Well, here I have a function in front of me, and this function, fn, has several lines of code, right? So we got a lot of code sitting here, and I come along, and all I need is these 3 lines of code. I want to reuse those 3 lines of code. What's the right thing to do? The right thing to do would have been to do an extract method refactoring, call that function right here, and then extract that function separately and bring in those 3 lines of code. But I'm scared to do this because if I do this, what if the code that uses fn ends up being broken? I don't want to take the blame for breaking some code. Oh boy, no, I don't want to do that. I want to take the path of least resistance, and guess what I'm going to do? I really need these 3 lines of code, so I'm going to quietly copy that, and way over here in another part of the system, I'm going to simply copy those 3 lines and quietly move on. See, I didn't break anything that worked. Well, that's a wrong thing to do. Why did we do that? Because we don't have any automated tests. Well, if you had had automated tests, we would do this refactoring that we did a minute ago, and the automated test will give us a very quick feedback that everything that worked before is continuing to work now, and yay, that's great, this refactoring is awesome, let's make it and move on. But unfortunately, because we don't have automated tests, we fear, so we tend to do the wrong thing rather than doing the right thing. So look around in your development practices and see if you have viscosity. And environmental viscosity, you fear doing something because of the environment, either colleagues who threaten you or environments that are hard to work with, or it's a technical viscosity where you are saying, hey, this code, I would rather duplicate this code, I would rather write poor quality code, I would rather let these warnings be in the code because it's really hard for me to do the right thing, and because we've not set up good practices that can lead us to this right kind of behavior. The next smell here is needless complexity. Now, needless complexity is that plagues every system we work in. People want to come build for extensibility, reusability, and support all kinds of structures. But why can't we just do the minimum code that gives us the behavior we understand and come back and add more code when we know what we are doing? So needless complexity comes in unnecessarily a lot of times because programmers are just way too eager to write code. I worked in one application where I was looking at a piece of code and the programmer takes a data from a database, 250 lines of code later, creates an XML representation, calls a function and passes this XML data, another 250 lines of code to parse it, only to reinsert into the database. Like, why do we have this complexity of XML processing here? The data is in this database here. It should be manipulated and put back in this table. Why do we have this XML transformation right in between? And he said, Venkat, look at the extensibility of Dot now. Isn't this amazing? No, it's not. Why do I care about XML right here? Where does the data come from? There. Where does the data go? Here. Well, why am I not just manipulating the data? Why am I going through XML transformation? Oh, Venkat, because it provides extensibility. Ultimately, you could send data anywhere and you can get data from anywhere. Wait a minute, But where are we going to send the data? What do we know right now? The future is unknown, but what do we know now? We know the data is here, and to provide this business value, apply this transformation and stick the data back here. And of course, we got to be this grandiose, extensible. So while he was saying this, I picked up the phone, started dialing, and after a second he says, oh, hang on a second, he says, hello? I said, hello? Is that you, Venkat? It's like, yeah. Why are you calling me? I said, look how extensible this is. I could be anywhere in the world and I could still talk to you. Why should I talk to you in person, right? Well, that's the kind of model we don't want to go to. So yes, extensibility is important, but understand what extensibility really means to us in the context of the application and the domain. Do not plan for extensibility you don't understand. If you write simple code, minimum code, you can provide that extensibility when you know what that is. Instead, if you build all these grandiose things, the extensibility that comes in front of you is not what you anticipated. And now the code you wrote actually is a burden to carry forward. So do not bring in unnecessary complexity. Don't try to solve every problem in the world. Understand the problem you're solving and solve that problem. And try to come up with simple solution. One way to make things less complex and more simple is to logically go through a sequence that is meaningful. Keep the focus in the code. For example, I'm sure you've seen your share of code like this. You look at a function, they tweak a variable here, they tweak a variable there, they do a bit manipulation here, they do a shift operation, and you're looking, it's like, oh, my hair torn. Why are you doing all of this here? We don't get it. But then you look at some piece of code and you are reading it and you just get it. There's a very logical sequence. You read this, of course I anticipate this to happen. The next step, that makes sense. The next step, that makes sense. So the point really is, I'm sure you've seen people explain things to you. Some people walk you through very nicely and you get it. Other people tell you stuff and you're more confused when you hear them. Why is that? Because the simple solutions and explanations take you from what you know and take you through one small unknown at a time. Whereas a complex code jumps around unknowns and you're not able to keep that in your head because there's too many context switch going on in your mind. So remove needless complexity. The next thing here is needless repetition. Needless repetition is where not only duplicated code, duplicated effort coming in the code. You make a change here and you got to make a change there and make a change there, and it ripples through the system. And you don't want to be duplicating configuration data everywhere. I once came across a client where they have a product, but the minute one of their customers purchases their product, it would take them, no kidding, 3 months to deploy their product. Why would it take 3 months to deploy the product? Because they got to change, I'm not kidding, thousands of configuration files because everything was ultimately customizable and extensible, but they got to change all these configuration files. Very, very expensive to deploy product. And that really took away a lot of their revenue because between they sign a contract, now they got to send engineers to the field to start customizing it. Terrible revenue path. We don't want to get into that kind of mess. So don't come into practices that require repeatedly doing stuff. Try to really minimize duplication and needless repetition. And the last smell is opacity. Opacity is where the code is really hard to understand. If a code is hard to understand, it is hard to maintain. Think about examples of code that's hard to understand. Well, here's an example of a code that's hard to understand. A very long method. How long have you seen methods? How about 12,000 lines of code in a single method? How do you understand what this method is doing? Yeah, we can write comments on the top, but usually the comments are misleading and out of date, and you're trying to read through and understand. Long methods are hard to understand. They are opaque. Coupling increases the complexity of code, and that becomes hard to understand. Lack of cohesion results in opacity as well. Poor variable names, poor function names, poor sequence of operations, convoluted operations, unnecessary operations, code that is going through several levels of nesting. All of these are examples of code that is opaque. If you read really good code, you would be shocked at how nicely modularized the code is. Function variable names are given nice, beautiful names. Method names are beautiful. You can read and understand what those things mean. You don't have variables like X, Y, Z, R, P, and J. They are meaningful names that are expanded. So reading like you're reading a text and becomes really transparent. A good code is transparent. You can see through. A poorly designed code is opaque. You cannot understand it. You lose hair trying to understand what this code is doing. So we talked about the 7 perils: rigidity, fragility, immobility, viscosity, needless complexity, needless repetition, and opacity. But as you apply some of the principles we're going to talk about in other parts of this presentation, it's very important that we apply some of the principles only when there is a force. In fact, that's true of design patterns. I really worry when people talk about design pattern because you can't really use design pattern in isolation. I want a force to really dictate that a pattern should be used. And to me, looking at patterns, ignoring design principles is not a good idea. So as you come to design patterns, for every pattern you look at, ask the question, what design principle is active? What principle forces us to use a pattern, and what principle shines when we use a pattern? Think about design principles, but there should be a force that leads you to use a design pattern. Likewise, also, there should be a force that leads you to use a design principle. If we use a design principle arbitrarily for the sake of using it, we would end up with one of the perils, one of the smells, which is needless complexity itself. So it's very important for us to apply these design principles we're going to talk about, but only when it absolutely makes sense and not otherwise. That's extremely important. So I'm going to stop this part right here, and we're going to start talking about specific design principles moving forward, and then look at some really good examples of it. But it's important to keep these design smells in mind as we go through the discussion of design principles, and then of course design patterns later on, and then during active design from there on.